I will now talk about the second LHC run, which Nima already alluded to. The best way of illustrating that we're now in a new phase at the LHC is this display of an event. This is a high mass dijet event, which actually has a mass of 8.8 tera electron volts, which is 10% higher than the energy we had in run 1. So this is experimental proof that we're now beyond the first LHC run. All right, so this, you know, so the LHC accelerator here in the Geneva area, and now in run 2, the energy is now 13 tera electron volts, nearly 50% higher than the first LHC run. The heart of the LHC are these LHC dipole magnets. So this shows a cross-section of them, one beam going one way around, one the other way around, and what is seen here is the complex magnetic field. The magnetic field, in order to keep these protons on the circumference, on the circular ring, they have to hold a field of 8.3 Tesla, and there's 1,200 of these. In order to hold this very large field, they need to be able to hold currents of 12 kiloamps. And this is done by using superconducting wires. You see here an example of a superconducting wire used in the LHC ring, and here you see how much this would be in copper. So that's completely impossible to construct magnets like that. However, the reason that we actually were limited in the LHC in the first run is because the connections between those magnets were not able to hold such high current. So we could only go approximately to half the LHC energy. And in the past 2 years, the interconnects between all these magnets were refurbished to ensure that they can actually hold the full current, so we can go to the full field and thereby to an energy of 13 to 14 tera electron volts. This shows pictures here of the ATLAS and CMS experiments, these very giant detectors. Here the ATLAS experiment with the two people over here, and here CMS, which is heavier than the Eiffel Tower. And this, I can't resist to show some of the pictures of these gorgeous experiments here. Now we also, so using these detectors and the LHC during run 1, we took a lot of data. This shows the data taking from that time. We took data here at energies of 7 and 8 TeV and proton-proton collisions with a total luminosity of 25 inverse femtobarns. And then the LHC also collides lead ions, either with each other or with protons. And in total, we took about 4 billion events each year, which corresponds to 5 petabytes of raw data. Using this, we made a lot of measurements. In total, the ATLAS experiment alone has published 484 papers to date, based on these 3 years of data taking, measuring basically, half of these publications are basically measurements of standard model processes, while the other half are searches for new physics. It's a very vigorous program of searching for new particles. This shows a summary of many of these measurements, which shows cross-sections for the production of many particles. So this is just inclusive proton-proton interactions. These are W and Z bosons, TT bar, top quarks, etc. And in all cases, you see the data here compared to the theoretical expectation. And all of these, the data agree actually with the expectation. One thing you can also see here is the Higgs, so where we've launched a measurement program, and we've actually got several measurements now in this already since the discovery. Now, just to give you an idea what really the experimental challenge is if you just imagine the most frequent process that any proton interaction occurs at all happens at the same rate as a pneumatic drill, then these measurements, these processes like W and Z production, they happen as often as like the Super Bowl. So they're like once a year. So this is what we have to dig out of all this pneumatic drill. And if you go to other processes like TT bar production or even raw rare, these happen like once a century. Okay? So that's really the experimental challenge, to dig out these processes out of all the frequent ones that we are not that interested in. Okay, so then, of course, during run 1, the big highlight was really the breakthrough from run 1 was the discovery of the Higgs boson, and I can't resist to show you here pictures corresponding to this. Here the Higgs in the diphoton decay mode, this little peak here, and here the Higgs in the 4-lepton decay mode, which Nima already discussed. And this was celebrated in 2013 with the Special Fundamental Physics Breakthrough Prize. You see here the prize winners on the podium. All right, so what do we now do from going from run 1 to run 2? So as I said, what was limiting us during run 1 was the ability to go to these high currents in the magnet to go to an energy of 13 TeV. So all of these interconnects were actually refurbished and replaced so that we're now able to go to this higher energy. And at the same time, several other improvements were made so that we can now also increase the rate of collisions per second from 20 million to 40 million. All of this together relates to the fact that, and we're running, basically the run is just started this year and is going until the end of 2018. So just as an example, so the Higgs boson, in run 1, we had approximately 50 events where the Higgs decayed to ZZ by 4 leptons, and in run 2 we have more than 700. So that allows us to enter the precision study phase rather than just the observation phase. Just to give you an idea, I don't want to go through this, but just to give you an idea, there's this humongous amount of work that was done. This is really incredible engineering here. For instance, here 10,000 splices were consolidated with 27,000 shunts, etc. So this was a huge amount of work. And we also, at the same time, we also improved the detectors themselves. So for instance, one thing we did is we have a silicon pixel detector very close to the interaction point, which in Atlas used to consist of 3 layers, and we've inserted a new layer, and this was largely developed here in Berkeley, actually, at only 3.5 centimeters. So this is the very first layer that any particle that gets produced in the Atlas experiment sees, and by going closer to this, before it was at 5 centimeters, we can better resolve whether the particle actually originated from the interaction point or maybe from a displaced particle decay. Okay, and so then what was very exciting for us was on June 3rd when we had the very first 13 TeV collisions in the experiment. In the beginning, we were a bit skeptical, looking at the monitors, is everything working, etc. But then there was a lot of happiness when we actually saw the first collisions appear on the screen like that. And we indeed even saw and this is very close to the experimentalist chart, we even saw our little 4th pixel layer producing hits right away in the first collisions. So everything is working very well. The experiments are functioning. So what can we learn in terms of physics now from run 1 versus run 2? What I'm showing you here is the relative ratio of the rate of processes as a function of the mass of the system that gets produced. So the protons interact with each other and produce a system X. For any proton-proton interaction, by going to this higher energy, we're not increasing very much. It's only an increase of about 10%. However, as we go to higher and higher masses, this increase becomes larger and larger. So for Ws, which have a mass of 80, it's about a factor of 2, as you can see here. For top quarks, which we produce in pair, it's approximately a factor of 4. But then for more exotic particles, supersymmetric particles like gluinos, which could have a mass of about 1.5 TeV, the increase is much, much bigger, like a factor of 50. Okay? So there we would have only produced 1 a month. This is not enough to discover it because there's also some background. Now in run 2, we would produce 50 a month. So, so we've taken data throughout the year. So this is here in beginning of June. This is when we started. And you can see that in the beginning, we were not actually increasing the data set very much until end of August. But since then, we've taken a lot of data. So this data set is not yet as large as we had in run 1. It's about 1/5 as large as that. But it is more powerful because of the higher energy. So in terms of its power, in some cases, it's already much more powerful than run 1. And we've recorded 1.7 billion events. I'll show you now some results which we have produced during the summer using approximately 2% of the total data of this year. So for instance, we measured the rate of this total proton-proton interaction cross-section, that proton-proton going just to anything. And indeed, we see here, so this shows this rate as a function of center of mass energy. There's many, many experiments have made these measurements since the 60s. And here, this is now the new measurement here, this blue point. And indeed, we see approximately a 10% increase with respect to what we saw before, as we expect. We also measured the rate of W bosons, where indeed we see this factor of 2 increase we were expecting. And also for TT bar anti-top production, we see approximate factor 3.5 increase. So you see here the energy of 8 TeV, which we had before. Now at 13 TeV, we've already made 3 measurements that agree with the, and they indeed agree with the expectation. Now, as Nima already said, one of the really important things that we want to do in the second LHC run, and even in the third and the fourth one, is to understand the Higgs boson in much more detail. So, for instance, the theory predicts exactly how the Higgs boson couples to standard model particles. It depends on the mass and on the type. And with theory, we can calculate exactly how the Higgs boson gets produced. There's several ways of producing it when these can be predicted with a good uncertainty. In particular, these can be predicted with an uncertainty up to 3%, this one more like 10%. And also our theory tells us exactly how often a Higgs boson decays into which particle, depending on it. So 58% into B quarks, 22% into Ws, et cetera, et cetera. So by measuring the Higgs boson in all its production modes and in its decay modes, we can constrain how the Higgs boson couples to the standard model particles. And this is our first, this is the summary of what we've done in run 1. At the moment, we have quite sizable uncertainties, something between 10 and 40%, or for some cases like the muon, we haven't actually seen that conclusively yet that it couples at all and have just a very large uncertainty. So in run 2, we should be able to improve the precision by how well we can test this by a factor between 2 and 3. Another thing we can try to understand is, for instance, whether the Higgs boson has anomalous decays to other new particles, for instance, to dark matter. So if it could be that the Higgs gets produced in association with a Z boson and then it decays to dark matter particles. So we've looked at that in run 1 already. We're looking by looking for a Z boson recoiling against nothing. And we see the data here compared to the hatched histogram is what we would see if there was some sizable production of this. And we already have learned that the fraction is less than 15% of all Higgs bosons decay in such an invisible way, but we should be able to test this in the future to 5% or so. And this is quite interesting. You will see later a talk by Tom Shutt about dark matter constraints. This is complementary to trying to observe dark matter directly in underground experiments by looking, so this is mostly working in the low mass region. It only works if the dark matter mass particle is less than half the Higgs boson mass, which is why it cuts off here. Something else we can do, as Nima already alluded to, is also find supersymmetric particles. We did not see them in run 1, despite trying really, really, really hard, with about 100 papers published by Atlas alone on supersymmetry searches. So what we're looking for is, for instance, one of the most interesting processes where you have gluinos being pair-produced, and these then decay, and we see, again, these chi-1 zeros. These are potential dark matter candidates and many quarks, which manifest themselves as jets. So we see multiple jets and something escaping, basically momentum balance not working. And so this is something we look for. And for currently the run 1 limits are, so we already know that these particles must have a mass bigger than about 1.3 TeV, between 1 and 1.3, depending on how they decay in detail. And in the future, we will be able to test the 1 TeV more. So basically, we're doubling the mass reach for such particles. One particularly important particle related directly to the hierarchy problem is the supersymmetric partner of the top quark, the stop. And here, so this orange area is what we're excluding right now, up to about 650 GeV, depending again on the mass of the neutralino, the dark matter candidate. And we will extend this significantly by also more than a factor of 2 in the future. We have already started actually looking for new physics. So as I showed you, we only have so far analyzed 2% of the 13 TeV collisions, just because most of them were only coming in the past 2 months, and we're really actively working on analyzing these now. So I can't show you the results yet because the analyses are not ready. But some we've already, with 75 inverse picobarns, already we were able to push beyond what we were able to do in run 1. So one thing we can look for is black holes, which evaporate immediately via Hawking radiation, and we look just at the total energy in the event. Black holes you would see at very high energy values here, but you see the data here consistent with the background expectation only, so no black holes yet. All right, so let me conclude that the LHC is exploring this very interesting fundamental scale of nature, the weak scale, and that this scale is full of mysteries, which Nima already discussed in much more detail. And the second LHC has started. We're taking data. Our experiments are working very well. We took approximately 1/5 of the run 1 luminosity, and we're analyzing this right now. And it's very, very exciting. So I would say, so initially the topic was to see whether there are any breakthroughs within the next 5 years. So run 2 is running in the next 4 years, so it's certainly possible. And then, for instance, Fabiola, who's now the director, would smile very happily, and maybe we can celebrate another breakthrough.